Hey, good morning. So we posted the homework yesterday. It was one day late, but we removed one question. So, so hopefully that will be fair. So today we start the neural network like as an introduction to CNNs, and what we have today and on Monday is nothing new. I mean, this is something that we saw before when we talked about ANNs and perceptrons, and we're just reiterating basically kind of the same concepts, and the notation, so really we can lead up to the notation that we have in CNNs is the main goal of today's lecture and next Monday's lecture. And that's actually the reason why we started with the classification, because, you know, the classification we had ANNs, now that will help us introduce CNNs in here. And then we had logistic regression that really helped us in regression. And nothing really kind of mathematically new. So we will not do any derivation. We will not repeat the derivations like normal equations, for example. We did that already in regression. But you will see all kind of different things that we have done before now. So the main message of today's lecture is just to look at the notations. I mean, that's really the main. And it's really worth it to spend a lecture on that, because it can get a little bit, you know, ugly when you have, you know, large feature space and then large number of data and classes and so on. So, okay. So I'll not really go through these introductions. I'll just keep it short, but this is really nothing but revisiting the ANNs, right? And we really look at the neurons, input, output, activations, and so on. Okay. So here is the unit, just to reintroduce these terminologies. Now, what you will see here about this neuron here, what we have as an input is the features, right? But remember, in a neural network, when you have hidden layers, the layers in the middle, not necessarily they have input features, but they will have the outputs from the neurons in the previous layer, right? So we will have kind of a couple of slides just about the features, and then we can generalize to any hidden layer neurons. But for now, for simplicity, we have seen this before. We have a neuron. We have input features on the left-hand side. We weigh every one of these features. So we have a weight multiplied by each one of these features. And these weights are basically, they're not the same weights. So each feature will be multiplied by a different weight. It depends on the learning dynamics. And then we sum, we add the bias, and then we have the activations. For simplicity, we can use linear activations, but to really get to the context in the data and the hidden information, we can use nonlinearity in here, and that's where the kind of the magic happens. And then we have an output. The output here could be the output of the whole network, or it could be the input to a next neuron in a next layer. Right? So we looked at this basically kind of as a fully connected layer, right? We have a fully connected layer where from one previous layer, for example, the output of these 4 neurons will be input to every single neuron in the next layer. So that's a fully connected layer. And these are the different activation functions. And we have seen this before. we dealt quite a bit with sigmoid and sine. And then once we go to the CNN, then we will look at tangent function, the ReLU, and the soft plus. Okay, let's bring the notation that we had before. So we have, again, this is a neuron for the first feature. So this is a single layer perceptron. We don't really have any hidden layer. So the inputs in such SLP or single layer perceptron is really the data, the features, right, is the input. So in here, we have the inputs, we have samples xi. For every sample, we have capital P features, as we have been doing for the last couple of months or so. And then now we have the weights. So now this weights, the subscript in here, it tells me which neuron. So now since we have one neuron, so this is W sub 1, and then the superscript in here, parentheses 1, it tells us which layer. So this means this is the weight vector for the first neuron in the first layer, right? And now that vector in here, dimension-wise, will be matching the dimensions of the input features. So since we have a dimension of capital P, then the dimension for this weight vector for the first neuron in the first layer is also dimension of capital P. And then we add a bias, and then the output from this this linear function is, we denoted this as H sub I1. So this is H sub I, meaning that this is really the output for the input for Xi, that's the ith sample. And then I have the subscript 1, that's basically the first neuron. And then the superscript of parentheses 1, that's the first layer. Okay, so we know now right away, this is really the output of the linear summation before the activation, right? We always look at things as, before activation and after activation. So this is before activation. This is for the first neuron, for the ith sample in the first layer, right? Or actually, it's the other way around. The output before activation for the ith sample of the first neuron in the first layer. Right? And then after that, we have the phi function. This is the activation function, and this is a function of the hi1 superscript 1. And now basically, this is the output in here. Now, since this is a single layer perceptron, then the output in here will be y, right? This is the output, right? So we have x input, we have y output. What is this output? This is the output of our model or perceptron or SLP for the ith sample of the first neuron in the first layer, right? So these are the equation-wise, and we have seen all of this before. So I will not really get into any of the derivations today, but just a reminder of what we have done before. So this is basically the vector heat transpose times xi. This is nothing but really multiplying this weight times that sample plus this weight times that sample all the way by plus this weight times that sample. This is really the whole operation here. And this is something I keep reiterating in the homeworks. Please don't just get overwhelmed with how the math notations look like. Go to the very simple, basically, principle of what we are trying to do. This is nothing but a weighted average, a weighted sum, right? Plus the bias. And this is basically after activation. Now, the simplest perceptron, meaning it can be even simpler for SLP, by using the activation to be linear activation, right? And then that means the output will be a binary between negative 1 or 1, right? So it's not between negative 1 and 1. It will be either 1 or negative 1. So it depends on this, the value of this hi1 here. If it's positive or 0 or it's not negative, then the output will be plus 1. If it's negative, the output will be negative 1. Right? And that's basically what the sign is about. Remember, when we use the sign as an activation function, we say the sigmoid between 0 and 1. Remember, basically you have 0 to 1, right? So if you have a very, very small number, the output will be 0. If it's a very large number, the output will be 1. And we said basically, what if we have output that have negative values, right? What happens in that case? So we use the sign in that case. And this illustration here just kind of tell you basically kind of visualization of how things look like. So this is really a copy from a slide that we had at the time. Okay, so now we can just reiterate exactly what we could do if we have a sigmoid function as the output, as the activation function. So again, this is, we focus on the first neuron, the first layer. So nothing really new in here. It's the same as what we had in the previous slide. Same thing for the bias. Same thing for the before activation output. And then after the activation, if we have a sigmoid, then basically the output here will be 1 over 1 plus e to the negative, the hi function. What you notice in here, another difference between this neuron and the one beforehand is that the output in here, we call it zi1, right? So now we are starting to bring this to be kind of hidden layers, right? So not necessarily the output of the neuron. This is not necessarily is the last layer. It could be multiple layers, right? So now we start to look at this as a latent space, or the output of a neuron as z sub i1. What this means? This means the output of the first neuron in the first layer to the ith sample. Okay, that's the output from this function. Okay, so now as a very specific example, if we have a feature vector of dimension 4, means capital P is 4. So xi will be xi1, xi2, xi3, xi4. And then we have a length, a vector of dimension or length 4 for the weights to match the dimension of the input. And everything else is basically as simple as what we had before, right? So the only difference between this slide and the previous one is that we have capital P, right? So far what we did, we started with input features, we output y, and then we just looked at what the dynamics and the notation is. And now we said, okay, maybe not the output is y, maybe it's zii, right? If it happened to be y, then zi1 superscript 1 is yi1. Okay. Now, let's move a little bit to the hidden layer and say what happens if we are in the hidden layer. That means I have an input, but that input is not really the input data set. It's not xi. What we have in here are the outputs from the previous layer, right? So now, what we get in here, if you look at this, so this again, neuron has the same components, has the sum, has the activation function, has the output, but now this neuron here is neuron J in layer K, right? You can see the output here is z sub I, j, to take a note, this is the jth neuron. So the superscript parentheses k means this is the kth layer, right? Now, we look at the input in here. So the input in here is not really the input for the data, like not the input of the whole network, which is the xi. This is in here, it happened to be the outputs from the previous layers, right? So now, remember what the outputs we had from the previous layers? It should be the output of a neuron is zi1. Since we are at the kth layer, so this neuron here is the kth layer, then these inputs in here coming from k-1, right? So the superscript in here is k-1, 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 right? And then again, we have the I, this is for the ith sample. And then we have, set the first one is the I sub 1, 2, and then all the way to this P to the k-1. This P to the k-1, it can be a little bit confusing, but what we mean by that, this is the dimension, the number of neurons you have in the k-1 layer, right? So the number of neurons you have in the previous layer, right? So the dimension here is P to the k-1. This is not really to the power. This is just basically a superscript just to denote that what that P is. Does this make sense? Anybody is not clear about this? Okay. Okay, so there is no relationship between, like P. I mean, this is something, and I'm very sure somebody will get confused about this. And we had students like actually a few of them last year where they spent a lot of time debugging because they assumed that the input P, this one, right, somehow it has the relationship to this P to the K minus 1. The numbers is not a numerical, value here. It's just basically a notation. That's all what we're doing. We're trying to say, again, the dimension here is of a P to the K minus 1, meaning this whole thing is just a one number. Simply, just even if you don't like this one, just scrap it and just say, okay, this is just the number of neurons in the K minus 1, as plainly as that. Okay, and then these weights in here, since we are looking at the jth neuron, so we have W sub j, and then we have how many of them? We have P to K minus 1, right? That's how many of them, because that's the number of inputs that we have to these neurons. And then we have the K in here, because this K in here has to do with the layer where we are at right now, which is the kth layer for this neuron. You can start to see now, when I'm looking at the neuron itself, I'm looking at the weights, which are really a characteristic of the neuron itself. Then everything in here is about this layer, K, right? And about the neuron, J. And in the inputs, they have nothing to do with this neuron. They are really an outcome from the previous layer, previous neurons, right? So we don't have K in here, we have K minus 1. I'm really emphasizing the obvious as much as possible because I know how much this can be confusing once you start to do this coding in the next homework. Okay, so a specific example here. Imagine that we have the second neuron in layer number 5, and then in the previous layer number 4, we have basically 4 neurons, right? So we have 4 neurons. That means I have 4 outputs from those 4 neurons in layer number 4. The notation for them is ZI1 in layer 4, ZI2 in layer 4, ZI3, 4, and so on. And then I have the 4 weights, but now I have this 5 in here, right? So I have 5 because I'm in the 5th layer. This is layer number 5. And then I have W2 because I am in the second neuron. This is my second neuron in the layer number 5. And then I have these weights. Multiply, sum, add the bias, and then I have the output, which is HI2 to the 5, meaning this is the the output from the summation linear operation for the ith sample for the second neuron in the 5th layer. Activation, I have the phi as an output, and this phi in here is nothing but the ZI2 to the 5. Any questions? Okay. So now, exactly just a review of what we have done before. Now, when we like to really kind of minimize the error discrepancy between our y and the predicted y's, right? And then next lecture we will have, a hidden kind of a whole neural network with 2 hidden layers, and then we'll have all these matrices and vectors in there, so that we can really see what are the input and the output for each neuron. But for now, I just want to review with what we have done before. Okay. So now, for a linear perceptor model, we can just look at what our target is to find the model theta, which is basically, in other words, what will be the weights W's and the B, the bias, right? And we can minimize the least square cost function. So the mean square error between the y, the ground truth labels, the ground truth classification labels or classes, and the predicted, which is y hat in here. Since now we have y, which is a matrix in here, because we are not really bounding ourselves only to a binary classification. So this is, we have nth of these samples, and each one of them will be representing by a logit based at the output. Then now we have a matrices for y's and y hats. So now we don't really take the L2 norm. The L2 norm for matrices is what? Is the Frobenius norm, right? So the Frobenius norm is nothing but the square root of the sum of the squares of the elements, or the sum of the absolute squares of the elements. It's just basically kind of the L2 for the matrices. Right? A simple form for it, the x times x transpose to the trace, that will give you the Frobenius transform. Again, this notation, if it's confusing to you, just understand what the Frobenius form is, and then you just, that's all what really matters. Don't get really kind of, confused by these notations if they don't really make you feel comfortable about them. Okay, so we minimize this, and we did this before. Either we have a closed form solution using normal equations, or we can use the gradient descent, right? And I will not go through the derivations for the normal equations. I think I hit those slides. We have almost 7 slides. Each one has 15 different lines. I can tell you basically it was a big turn-off for the students last year because it's just the mechanics of things. The concept-wise is normal equations. What we did in regression, exactly what I wanted to understand, right? And here is basically kind of projecting that into this matrix notations here, just for simplicity. Okay, for a simple case, single layer, single neuron, linear activation function, then we can really, the matrix W, because remember, what the difference in here, when you look at the model, your matrix W has all those weights, right? But now we are just making it very simple, and that weight, that matrix becomes a symbol, basically vector here, right? Column vector, we call the column a single column matrix. Okay, so this is the bias. These are the outputs in here, and again, since we are already having a very simple single layer, single neurons, then this will basically boil down to just a vector, not really a matrix in here. And then the input matrix is dimension NP. The output prediction Y is dimension N times 1. And then the output prediction will be X times the W plus the B, 1 and 1. And basically, I'm just having this highlight in here just to refer to the fact that we have single layer, single neuron DNA activations in here. Okay, and now we can really minimize the mean square error in here, take the derivative to 0, and do all of that, and then this is what we will get as the output. This is the normal equation that we have done before, right? So now from here, we have a closed form solution that calculates our weights for all layers, in this case, and we have the input X, and we have the ground truth Y's, okay? So that's the normal equations, and we did this before. Do you remember what was the problem with normal equations? What was one of the cons that we said, okay, maybe it's a better idea to look at the gradient descent? Anybody can remember?
It can't solve the non-convex.
Yeah, sorry, there was 2 people talking from Virginia, one from here. Yes, you're right. It's the inverse, right? When you have the number of features grow, right? When you have a large number of features, right? And remember, we'll have now, like 1,000 by 1,000 matrix to take the inverse of, which becomes an issue, memory-wise as well as processing-wise, right? And if you have some noise, then you will hit some singularity, but we will not really worry about that in this course. However, an iterative fashion, so you really have kind of a training based on how much you're really getting closer to the local minima, is the gradient descent. And that's basically what kind of have been a de facto, especially when you don't really have big assumptions about the bias, because we have assumption here that bias is equal to a 0. Okay. And we did this before, right? Everything in here, again, just look at this as a review. If any of these slides is confusing or new to you, that means you have to go back to either regression or classification to look at the corresponding slides. So these are the updates for the weights. We have the weights at the previous iteration T minus the learning rate times basically the gradient of the loss function in this case. And basically it happened to be of this form for the specific scenarios. Okay. Now when we bring the bias, then we bring basically this matrix in here, and I think I introduced it somewhere. Yeah, I think I introduced it before. Yeah, here. Look at this matrix in here. Oh, this is nothing but really n by 1. This basically has a vector of all ones, right? So all ones. And basically the idea in here, it just, since B is just a vector, we like to operate on a matrix. So we multiply basically, because Y is a matrix, X times W is a matrix, B is a vector. We bring this W, so we can really create what? Take B and just repeat it. That's all what we are doing, right? So this matrix in here of all ones, or this vector of all ones, is basically taking the B and just repeating it, so we can make a matrix. That's all what we are doing, right? So the notation can be correct when we add them together in here, dimension-wise. Again, the transition between what we have done before, vector-wise to matrix-wise, is the only thing new in this today's lecture and next lecture. So that will help us quite a bit when we talk about CNNs. Okay, and then now we have the mean square error as before, but now we have the B as a vector in here. So we have an update for the bias as well, which is basically minus the learning rate with the partial derivative of the loss with respect to the B, which will give us basically this equation in here. Okay, so in terms of concept, absolutely nothing new. And again, you can see the hidden here. I'm not really sharing basically the how we went from this here to all the way to these equations. It's a little bit mechanic, and I really don't want to get us confused about that for now. Okay, so what really matters in here? For the gradient descent, we need to initialize the weights and the bias, right? Create a convergence criteria or condition beforehand, and that criteria could be that the loss after every epoch is less than a certain threshold gamma, or beforehand I just say the number of epochs I'm interested in is like 400, for example. But usually the first one is really what really kind of look at the learning. And of course, you remember when we talked about the validation curve and the test and training curves, how the gap between them, it means you are overfitting or underfitting, all that we did in the regression. That comes into play when you look at the criteria for convergence when you are babysitting the training. And you will get your hands dirty with those stuff once we have the CNN covered. Okay, so after we have initialization, now we can calculate the predicted output matrix, because now we have the W, we have the B. So we can predict the output Y could be predicted as X times Y, W transpose. And you can see in here, we have everything. We have all the data, we have all the weights for all the layers all together, and the biases, right? And then once we have that, now we have a prediction Y hat based on the initialized W and B. Now we can calculate what would be the update for the weights. So, and this is the equation for the updates. This is from the ground truth. This is from the data. This one here is the predicted one from this step. And then these ones in here from the initialization, the weights. The same thing for the bias, right? We didn't really meet the criteria. I go back, and now I calculate a new Y hat based on the new W, T plus 1, and the new B, T plus 1. Now I have a new Y hat. Now I have a new update for the weights, a new update for the bias. I see the criteria. I'm not meeting my criteria to be less than a certain number gamma. I go back, I calculate Y hat, and I keep doing that until I converge in that case. And remember, basically, this is basically where we have all the samples are really, we do this for every single sample, right? If we do that. Now in the batch, remember the batch gradient descent? Remember that one? Where we split our data into a number of batches, and that's this kind of criteria. So the learning curve in here, alpha, right? The number of batches, B, is also is a parameter that you have to predefine. And then you do this not for the entire, the X dimension will be smaller. Now the new X dimension here, if we have a batch, will be basically what? The number of samples I have in every batch, right? And that will cover my epoch, and then I keep doing that. So now one epoch will have a subset of the samples, not the entire samples in this case. Any questions? Okay. Here is a kind of a toy example, and we have some codes next, so you can really kind of start just kind of to understand what's really happening. You can really implement these at home. So imagine that we have X to be of this dimension 10 by 2, right? So we have this here, and then I have this one here. These are two columns, dimension 10 each. The output of dimension 10 as a vector. Then how many weights do I need? I have 2 of these, right? So all what I need in here, I have 10 samples, right? I have 10 samples. Each sample has 2 features, right? And I have a label output for each one of these samples. So I need 2 weights. I need a bias, right? Now I can really calculate what will be the y hat in this case. And then the mean square error loss is defined by this Frobenius. In this case, this really translates to what? L2 norm, because our y is just a vector, right? But if you have multiple output, then that will not be the case. Okay. And then we have the update weights for the gradient descent, and the same thing for the bias based on what we just covered in the previous slide. And now you just basically implement this. So this for the batch gradient descent. This is the pseudocode on the left-hand side. Actually, this is the code. And then I just want to really highlight some of the things on the right-hand side. So imagine that we have at iteration number 1, we have an accuracy of 0.5, and the loss is 35.6. The updates that I have that I multiply basically by the alpha is basically 67.7, 56.35, and for the bias 8.1. At iteration number 120, the training accuracy improved to 0.8, and the loss really became smaller to 0.1104. And you can see in here, the update, the gradient values in here are much smaller than here, right? So we're really going really quite a bit into the right direction in this case. Okay? Any questions? Okay. And this is something we already covered quite a bit in detail before, and you will revisit this again in the scene and homework that you'll be busy with after the exam. This is the batch, mini batch, and the stochastic gradient descent. Right? Okay. The batch is basically for the entire sample, the mini batch for the B, like a subset of the samples, and the stochastic in here. Every single time, every epoch, we just pick randomly a new data sample, right? And that's why you remember that curve that I showed, basically in the stochastic gradient, you just jump around, right? You keep jumping around, you're not really converging and smoothly, right? And the mini batch is in between. It's not really as expensive as the batch gradient descent, but it's not really as chaotic as the stochastic gradient descent in this case. Okay, so this is basically just to put the algorithm into perspective. And again, you just look at these numbers in here. We set the 0.2 for accuracy. We jumped to 0.8 in 60 iterations. Remember when we had 120 iterations in this one here. Remember that one? 0.5 to 0.8 for the batch gradient descent. And here we started much rougher, like 0.2, right? But we also converged faster to the 0.8. You see that because of the mini batch that we covered. Is it always the case? No. It depends on the mini batch or the batch that you're already using to go to 60 iterations. But it's cheaper. And this is the stochastic one, right? The stochastic one, it took again 120 iterations to go to the same accuracy level. But we started in between, right? We started in between. But the path to it is very chaotic in here. So I found this very interesting. Let's see if I can open it. Yeah. I hope you can see it. Very, very interesting, interactive, JavaScript-based, where you can interact with the web browser. I'm not sure if you have seen anything like that. If you have seen any such demos, please share it with us. You can share it with the rest of the students. Let me see if I can make this larger. So this is very interesting because you can still start to kind of play with things and just kind of help you understand what's really happening in here. So at the very top in here, you have a counter for the epoch. Once you started, then it will have a counter. And then you have a choice to basically for the different learning rates. And you can see for very obvious reasons, they have predetermined the values here because it may break the code if you use certain values, right? And that's actually what they have in here. Don't worry, you cannot break it, we promise, because it's the values here are free. But definitely, if you choose this one compared to this one, it will be much slower. Different activation functions, 4 of them in this case. And remember the regularization that we did before? You remember that? When we add the L1 or L2 norm to our equation for the loss function. They have L1 and L2 as well. How much the gamma, remember that gamma that multiplied by L1 or L2 regularized term. Also, they predetermine that value. And then what will be your application, classification or regression in this case? And then here we have 3 different data sets. And you can see this one is one of them. This is the second one, which is an easier one because they're really linearly separable, right? There's this one, non-linearly separable, and then you have this one, which is really a tough one, right? In here. So you have 4 different data sets. And now you can really choose the ratio of training to this data. You want to use 50%, 30%, 70% of the data, or not. You want to add some noise to your data. You can see that. See if the noise, the data is not really as perfect as it was before, right? You see that in here. And then the batch size. When you use batch gradient descent, like what will be the batch size in this case, right? And you can regenerate that for every single data that you have in this case. Okay, let's keep it just noise-free. Yeah, see, if there's noise-free compared to noisy, it becomes much more challenging. This is doing it for every single sample, like every single sample is a batch, right? And you can make it like a 30 in each batch. Okay. Now, what are the features that you use? You have x1, x2 multiplication. You have the sinusoid. And you can have the choice. You can really choose just to use x1 and x2 for simplicity. And then for the hidden layer, and here you can choose how many hidden layers you want. I'm not sure if there are a limit. I think 6 is the limit in here. And then I think 0 is the minimum. So if you use 2 of them, hidden layers, for each hidden layer, you can really have different neurons. So you can really decide on how many neurons you want. The same thing for the second layer. You can choose how many neurons you have. And then in the output in here, these are the samples. But you can see in the background, this basically tells you how the algorithm is really classifying, right? Different classifications. So this is showing you the test data, and this is basically the training data in here. Okay, and I think we can run it, let's say. Yeah, it's doing very well, very quickly. You can go back. You can see from here, the learning curve is very quickly basically converted. You can see it's very, very nice. You can repeat that, but now you want to add some noise, and then you do the same thing, and you can see there are some noise in here. The algorithm is taking quite a bit longer. You see how it's going to tweak. We looked at this from the support vector point of view, right? And the same concept is still valid in here, right? These support vectors, meaning those ones close to the boundary between the two classes, right? Those are your robustness element. These are the ones that really make, the further you have them away, the better it is for your robustness algorithm. And the good thing about this, we can really come here and look at the weights, right, being calculated. And the thickness in here is a ratio of the weight itself. So you can actually go here, and you can change that. You see that? I'm going to make this 0.1. You see how I really damaged that? You see that? You can really change the weight and see basically how important this weight for this new output in here. So these outputs in here are the ZIs in here. What else? Let's use linear. Okay, what do you see now? Was a linear activation, right? Then the boundary in here just a linear, is a line, right? Because we have 2-dimensional, right? A plane for the 2 features. Then this one here is just a line. That is different from when I have sigmoid. Right? Okay. So I think I found this very, very useful actually, just for you to get a intuition about what's really happening. Yeah, if you add more features, let's say the sinusoids, for example, you can see the sigmoid. Do this. You have more participation into your linear here, right? So the score in here 0.063. 0.039 for the testing. You add quite a bit of noise. See, the loss is higher, right? It was 0.06, now it's 0.1, yeah, getting there, see? In 700 epochs, we're getting there. Keep doing this. You see, we have still some errors in here, right? Because the background is orange, that means these ones which belong to the blue, they are classified as orange, and these ones here classified as blue, but they are really orange. The test data, the test data. Okay. Any question about this? So the link is on Canvas, so you can really get to it from there. Yes. Yeah, so how you decide the number of neurons?
Yeah, like, is it always like?
No, I mean, not necessarily, right? I mean, it depends on how much you want to represent so you can really have 8 in this case, and we can do that. So let's really say, let me repeat that. So let's do 4 of them, okay? And now we have noise really highest, 50. This is the simple data. And then let's see, run and see basically what will be the best test loss that we can get.
If you have in the second layer with the 2 neurons, how do you get from like 4 outputs and then get it down to 2 inputs?
Yeah, well, let's do that. So let me add here just 2 more and see in how many inputs we can get to the same. Did it help much? Little bit, not really much, right? We got to the same 0.099 around 400 epochs. Right now it takes more because you are the main concept behind what the number of neurons, but you are trying to represent your manifold, your subspace where the data is, right? You want to have more, freedom, right? More degrees of freedom to find that manifold. When you add more layers or more neurons in general, that means you are expanding the architecture of your model, the capacity of your model, which means that in order to avoid overfitting, you need quite a bit number of data, right, to explore that. If you don't, and you have very, very complicated architecture, a lot of neurons, but you have small number of data, then you will have overfitting. And that's the problem, right? Now, is there an exact science on what will be the optimal number of neurons and stuff? No. There's quite a bit of ad hoc. And over the time, basically, people start to look at the backbone, like ResNet and AlexNet, and these are the specific networks that we know basically these are working in their applications. But now, if I add this in here, right? At the end in here, what I will have just basically all of this will map the last layer, and we'll talk about this in scene in much more detail. All what these neurons are doing are creating the feature space. And then I have to have a layer at the very end that map from this feature space into the number of classes I have in here. So that will be the 2 classes, right? In this case. So if I do that in here, then you can see from here, I have this one, the thickness tells me this one is really very important. This one here, and this one here, and this one. The rest are not that. This one, for example, is not very important in that determination. You see that? Did I ask a question? Yeah. So the variation of the features in here, right? Look in here. Like, for example, if you increase the number, I fix the number of features, like this here 4, right? I keep increasing the number of neurons in here, right? Now, how much you have information at high level, low level to high level? Usually, the first layer, right? The first layer will have the element, like the first derivatives. Like if you have an image, you have a line, right? You have a line, edges and lines and maybe colors. That will be the first layer, right? The next layer will be something more important than that. Like, for example, look at the face. The first layer will be basically kind of, the lines that where we have different, intensity edges between, different colors, for example. The next one will have a little bit more information. The last layer, for example, will be a very, very high context, high level, the very high level information, not the low level specifics, right? So now, for the first layer, how much do you, like, for example, if it's only about lines, right? How many degrees of lines you are looking for? Are you looking for horizontal and vertical, 45 degree? What are the all different ones you are looking for example? And in the neural network, with the training, it will figure that out. The more neurons you have, the more lines, and we'll see that in CNN. We'll have some examples to show you visualization of how the weights will look like. The weights will really look like lines, like literally lines. It depends on the data, of course, but will be lines. And then the more of them, then you will have different lines being depicted, learned by the network itself when you're doing the back propagation. Right? Now, how deep you want the network? Again, it's the default that the deeper, the more you explore, but that means you need a lot of more data, right? My problem with that approach is that the more hidden layer you have, the less you know what's happening. Right? It becomes much more complicated, and people just say, "Oh, yeah, it works." Yes, of course. I mean, you have much more hidden layers and much more data. Yes, eventually the network will figure it out. But do we know what's happening? No. I mean, it becomes very difficult. There's quite a bit of research, and I'm really hoping to spend 2 weeks in this semester in April to talk about what are the different tools that you can have to have kind of an X-ray of what's happening in the neural network, like visualization tools, different things. So we'll start talking about those in March through April. What are the different techniques? But the default, if you see, there's quite a bit of trend, especially from companies like Facebook and Google, and because they have the computation power, they have the data, they have very, very complicated neural networks. And they do the job. I mean, if you focus on performance, yes, I mean, you have very complicated ones. But in real life, will you be able to deploy them in real life applications at the edge network, at the edge of the network? That's the question. And then when something goes wrong, like for safety applications, if you don't understand what's happening in the network, then it's very difficult to understand why it went wrong. And that's where the robustness element comes into play. So many amazing neural network in the lab works very well. Take them to real life applications and they fail miserably because of the robustness element, because of the complication, how complex they are. And it's very, very complex for us to understand what's happening in there. So there is a design element to it to decide on the number of neurons and the number of hidden layers. But for example, just keep doing this. Look at the loss, like 0.517. See, I added all these 6 hidden layers, and now the network basically, because the capacity of the network is very, very high, right? But I don't have enough data, right? So the network is still, the loss is very, very high. And it's not learning much. Now, if I reduce this, I repeat the same thing. It's trying very hard. It's not getting there. See, there's saturation happening. Even you get to 1,000 epochs. Why? Because you don't have enough data to explore all this. And you can see from here the weights, the thickness of these lines. You see, basically, they're not really helping much what's happening here. So you have a saturation happening in here. Feet. Same thing. The network is very, very complicated. Still very complicated. Now things are working. And remember, the network is really, when you have, very, very lazy, right? It will find the shortest path to find the ultimate solution, even if that's not robust. That's one of the problems with your networks. And I will show you one of my former students in his thesis work, like from 4 or 5 years ago. He has this kind of, and hope he's a postdoc now. He will come and teach a couple of classes because he has a very nice explanation of neural networks. For example, he has this kind of exploring what the neural network capacity using questions, like abstract questions, like, why he used the famous, why Bugatti not BMW, or like this kind of questions. And then the network will really kind of tell you where in the image it decided to be, this is Bugatti, not a BMW, for example. And one of the very nice examples is he has a stop sign, like you have traffic sign. The whole data is traffic signs, right? And now the traffic signs, like all of them, we have a circle, right? The stop sign is the only one with the polygon, right? Stop sign, right? So now when you're saying, why did you decide for a neural network? Why did you decide this is a stop sign, not a turn left, for example? What we expected is that the neural network will say, oh, because of the STOP is written there. The network actually didn't do that. The network just found the polygon on the corner and said, okay, all the other data don't have that, so this must be the stop sign because it has that. It did it right? But it's the laziest approach, right? I mean, it's the simplest, and nothing wrong with that. But that's something we have to keep in mind about the neural network when they decide on things. But I think this tool in here is very, very cool. I think it really gives you quite a bit of intuition, just play with. And the link, you can find it on, here. I have it here on Canvas, so you can look at that. Okay. I think that's all what I have for today. The next time, then we'll move a little bit closer to the CNN. I will have the matrices notations in there. And then after that, we start with the CNNs. And then after that, we start to... the math part of the course, I think, is very mild moving forward. It's really more algorithm, more architecture. But what we learn in the math, I'm hoping it's always in the back of your head when we look at CNNs from now on, because without that, we don't understand what's happening in CNNs. But more and more architecture, more high level. And then after CNN, we'll go to, what are the best practices to train a CNN, different architecture, and just like more hands-on from now on in the course. Even more hands-on than what you had hands-on before. But yeah, it's... Okay, please, for the new homework, please start today. If you haven't started, start tonight. It's really important this year. Okay, thank you, everyone. We'll see you Monday. Have a good weekend.
Thanks, Professor.
May I have a question about the W? Like,
yeah, can you say it again?
may I have a question about the W? Like, why is a matrix instead of a vector?
Yes, we will look at that actually in more detail next time. But you look at this as a whole network, as a whole architecture. So for each neuron, you will have a W, right?
Oh.
So now for each layer, you will have multiple Ws, multiple vectors. Then for the whole network, you will have basically Ws of different matrices for each layer. You see that?
So like in future, like we will explore like some like matrix W for each layer.
Yes, exactly, yes, because you have different neurons there. Yes.
So but like the weight is attached to neuron, right? So like there's only a vector of the weight. There's no
so
matrix
for
of
each
them.
column, it will be associated with a neuron. See that? Each column W in the matrix W is not really a new matrix. It's nothing but we are concatenating the vector W's, one for each neuron.
And another question about the batch and mini batch part.
Yes.
Like why did like mini batch only take like 60 iterations to get to the very low loss?
Yeah, because you have some batches, right? So now when you sample the batches, it just happened in here. When you are sampling, you don't really have. Remember, in the batch, not the mini batch, the whole data, like the phase algorithm you have, at every epoch, you really try to do it for every single data sample you have in your data, right? So that will take you 100 something, right, to get to get to your solution. In the mini batch, if you really just you take subsets, so you don't really have to wait for the entire data. You just take a batch, which is a subset of the data. That will get you. And remember, go back to the slides where we showed you the convergence of these three algorithms, and you will notice from there in the mini batch, you will get very quickly to the neighborhood of the solution. And then once you are in the neighborhood solution, to go to the optimal solutions will be very slow, right? Not like you look at the entire data. At every epoch, you are run this on the entire data. So you move slower, right? But it's almost steady to the optimal solution. And in contrast, when you have the stochastic approach, at every single epoch, you have a new sample. So you keep jumping around. So you don't have a smooth convergence at all. You cannot describe it as fast or slow, but it's very chaotic, right? And that's basically kind of the problem with the stochastic one. But the mini batch, you really move very, 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 very quickly to the neighborhood of the solution, and then once you are there, it will become much slower to get to the optimal solution.
Yeah. Okay. So but for every iteration, mini batch will take less. Comparing to batch gradient descent, mini batch will take less data set per
Fewer, yes.
iteration. But
Yes.
yeah, but each iteration it will perform quicker. But why did it take less iteration to get there? Because
Yeah, because remember, in each iteration you have a number of epochs, right? And the number of epochs depends on the number of data that you incorporate into your data, right? So now the number of iterations is basically how many steps in the optimization algorithm we got there. Right? You see that? Now it doesn't tell you basically how many data samples you have in each one of them.
Yeah.
Yeah. So that's basically what's really happening in here. And also, I can rerun the same code, right, for a different data sample, like something different, and then I may not get the same performance. So this is just an illustration for typical data, simple data, not much noise. This is usually what's really happening. So if you are okay to stop at a quasi-optimal solution, the mini batch will get you there much faster than the other two algorithms.
And another question about the configuration of neural network, is there kind of particular way that we could configure the hidden layer, how many neurons and how many neurons and how many in each hidden layer?
It's more art than exact science. It's as far as you have some general rule of thumb, basically about not to have too many neurons if you don't have enough inputs to it, right? And then usually you want to explore much more at the lower end than what you have at the higher end, right? And we'll look at that different architecture in CNN. We'll not go into deep like in UNet and stuff like that, but we'll look at ResNet, AlexNet, some of the famous architecture, how they look like, and the progression from simple hidden layers to complex stuff like ResNet, for example. So we will look at those when we talk about the architecture in CNN, maybe in a couple of weeks.
Okay, great. Thanks.
You're welcome. Okay, bye everyone.
Bye. Thanks.